Planet Semicon welcomes you to explore the field of semiconductor physics and technology, the foundation of microelectronics and VLSI design engineering.
In continuation to the part 1, we now move to the practical aspects of power integrity. This section focuses on IR drop, voltage droop, electromigration, clock distribution, and the design techniques used to build reliable, high-performance ASICs. So let's get started. This slide shows the major physical components of a typical processed VLSI chip. Around the chip boundary are the I/O cells and power pads, which provide external signal and power connections. The central standard cell core contains logic gates, flip-flops, and clock buffers that perform digital computation and account for much of the dynamic power consumption. Large memory, digital, and analog macros occupy dedicated regions and have their own power distribution. The power distribution network, consisting of rings, straps, rails, and vias, delivers a stable supply voltage to every active circuit. The clock distribution network synchronizes the operation of all sequential elements and is itself a significant consumer of dynamic power. Understanding the function of these physical blocks provides the foundation for studying power integrity and clock distribution in the following slides. Interconnects provide the physical connections between the various components of a VLSI chip. They carry signals between functional blocks, distribute clock signals, and deliver power through the power distribution network. The electrical characteristics are determined by the material properties and the structural dimensions. The intrinsic and parasitic RLC parameters impact signal delay, dynamic power consumption, and timing performance. They also contribute to IR drop, noise coupling, crosstalk, and power integrity challenges. As technology scales, interconnect design becomes increasingly critical for power efficiency, signal integrity, thermal management, and long-term chip reliability. The power grid is a hierarchical network that distributes a stable supply voltage throughout the VLSI chip. At the top level, the global grid receives power from the package and spreads it across the entire die using wide metal layers. The intermediate grid consists of trunks and straps that transfer current efficiently from the global grid to different functional regions. The local rails within the standard cell rows provide the final power connection directly to the transistors. This hierarchical structure minimizes voltage drop, balances current density, and improves power delivery efficiency. Power flows sequentially from the package through the pads, power rings, global grid, intermediate grid, and local rails before reaching every active device. A well-designed power grid is therefore essential for achieving good power integrity, stable operation, and reliable chip performance. This figure illustrates the hierarchical organization of metal interconnect layers used in a modern VLSI chip. The lower metal layers, M1 and M2, provide short local connections between transistors within standard cells. The intermediate layers connect logic blocks and route signals across functional regions using orthogonal routing to reduce crosstalk. The upper metal layers are wider and thicker, carrying long-distance signals, clock networks, and the power distribution grid with lower resistance. Metal layers are interconnected through contacts and vias, enabling vertical electrical connections between routing levels. This hierarchical routing structure improves performance, reduces routing congestion, and enables reliable signal and power distribution across the entire chip. Power is one of the most critical factors governing the performance and reliability of a modern VLSI chip. Every transistor requires a stable and noise-free supply voltage to switch correctly and meet its timing requirements. The power distribution network, or PDN, delivers this supply from the package to billions of devices across the chip. As technology scales, increasing transistor density and switching activity demand higher current from the power grid. However, interconnect parasitics introduce voltage drop, power dissipation, and supply noise that degrade the quality of the delivered power. These voltage variations directly affect circuit speed, timing margins, signal integrity, and overall chip performance. The power delivery network, or PDN, distributes electrical power from the package to every active circuit on the chip. Power first enters through the pads, which receive the external VDD and VSS supplies from the package. It is then spread uniformly around the chip by the power rings, before being carried inward through the power mesh of trunks and straps. Finally, the standard cell power rails deliver a stable supply voltage directly to the transistors in the logic core. This hierarchical network minimizes IR drop, balances current flow, and reduces supply noise across the chip. Since every logic gate depends on a stable power supply for correct switching, an efficient PDN is essential for achieving good power integrity. This slide illustrates how power is distributed within the chip core through a hierarchical network of straps, rails, vias, and decoupling capacitors. Wide power straps carry large currents across the chip with low resistance and distribute power from the global grid. These straps feed the local power rails, which provide the final VDD and VSS connections directly to the standard cells and transistors. Vias interconnect the metal layers, allowing current to flow efficiently between the different levels of the power network. Decoupling capacitors, placed close to active circuits, supply instantaneous current during switching and reduce supply voltage fluctuations. This hierarchical current distribution minimizes IR drop, balances current density, and prevents localized heating. Every metal interconnect, via, and contact in the power distribution network possesses inherent parasitic resistance, capacitance, and inductance. Parasitic resistance causes IR voltage drop, power loss, and self-heating as current flows through the power grid. Parasitic capacitance increases the charging and discharging current, resulting in higher dynamic power consumption during switching. Parasitic inductance generates voltage spikes and transient supply noise, particularly during high-speed switching events. As switching current increases, current density also rises, accelerating electromigration and reducing long-term interconnect reliability. These parasitic effects become more significant with advanced technology scaling, higher operating frequencies, and greater circuit integration. Power integrity refers to the ability of a VLSI chip to deliver a stable and noise-free supply voltage to every transistor during all operating conditions. This is achieved through the power distribution network, which carries VDD and VSS from the package to every active device on the chip. However, interconnect resistance, inductance, and large switching currents introduce IR drop, dynamic voltage drop, and supply noise. If the delivered supply voltage deviates from its specified limits, circuit speed decreases, clock jitter increases, and timing violations may occur. With technology scaling and increasing transistor density, maintaining stable power delivery has become a major physical design challenge. To overcome these issues, designers optimize the power grid. Static IR drop is the voltage loss that occurs when current flows through the resistance of the power distribution network. As current passes through metal interconnects and vias, part of the supply voltage is lost before reaching the logic cells. This voltage drop is more severe in long, narrow interconnects, high current paths, and densely switching regions. Higher temperature further increases metal resistance, making the IR drop even larger. A reduced supply voltage slows transistor switching, increasing propagation delay and reducing timing margin. Excessive static IR drop can lead to setup and hold violations, negative slack, and even functional failures. Therefore, Careful power grid design with wider metals, sufficient vias, and low resistance routing is essential to minimize static IR drop and ensure reliable chip operation. Dynamic IR drop, also called voltage droop, occurs when many transistors switch simultaneously and demand a large burst of current from the power distribution network. This sudden increase in current creates rapid dip by dt, or current change effects, as the power network attempts to supply the switching circuits. Because the power network contains parasitic resistance and inductance, these current surges produce a temporary drop in the supply voltage. The relationship V equals L times dip by dt explains how inductance generates voltage noise during fast switching transitions. The severity of voltage droop depends on switching activity, load capacitance, and the impedance of the power delivery network. Excessive voltage droop increases gate delay, reduces timing margins, and may cause logic failures in heavily switching regions. Therefore, dynamic IR drop is minimized using a robust PDN, decoupling capacitors, low impedance routing, and controlled switching activity. Modern VLSI interconnects must carry large currents while maintaining low resistance and reliable power delivery. Earlier technologies primarily used aluminium, while today's advanced chips predominantly use copper because of its lower resistivity and higher current carrying capability. Copper safely supports higher current densities, allowing narrower metal lines without excessive voltage loss. To ensure reliable operation, every technology library specifies the maximum allowable current for each metal width and layer. During physical design, these limits guide metal sizing and power grid implementation. If these limits are exceeded, long-term reliability problems such as electromigration can occur. Current density represents the amount of current flowing through a unit cross-sectional area of an interconnect. As technology scales, metal wires become narrower, increasing current density and the resulting electrical and thermal stress. Over time, this stress causes electromigration, where moving electrons gradually displace metal atoms from their original positions. This creates voids, which can open the circuit, and helix, which may short adjacent metal lines, as illustrated in the figure. The degradation increases wire resistance, slows signal propagation, and eventually leads to functional failure. Physical designers minimize this risk by limiting current density, using wider metal lines, increasing via count, and selecting appropriate interconnect materials. Electromigration is therefore one of the most important long-term reliability challenges considered during VLSI physical design. The clock is the fundamental timing reference in a synchronous digital design, coordinating the movement of data between sequential elements throughout the chip. Every register launches and captures data based on clock edges, making clock quality critical to correct circuit operation. The clock period determines the maximum operating frequency, while the clock waveform defines the timing characteristics of the clock signal. Practical clock networks also exhibit latency, skew, and jitter, which influence the available timing margin for data propagation. Clock uncertainty is used to model these variations and ensure robust timing verification under real operating conditions. Transition constraints control the rise and fall times of clock signals to maintain signal integrity and predictable timing behavior. Source and network latency account for clock propagation delays from the source to the destination registers. During STA verification, these clock parameters are incorporated into setup and hold timing calculations. Accurate clock definition and constraint specification are therefore essential for reliable timing analysis, timing closure, and successful silicon implementation. The clock tree network distributes the clock signal from a single source to every flip-flop on the chip with minimum skew and balanced delay. It consists of the clock source, buffers, interconnect wires, and clock sinks arranged in a carefully balanced tree structure. Buffer insertion restores signal strength and ensures that all sequential elements receive the clock edge at nearly the same time. This synchronization is essential for meeting setup and hold timing requirements and achieving timing closure during static timing analysis. Since the clock switches every cycle, the clock network is one of the largest contributors to dynamic power consumption in a VLSI chip. Excessive delay imbalance produces clock skew, which can lead to timing violations and unreliable operation. Therefore, clock tree synthesis, or CTS, optimizes the network for low skew, controlled delay, and reduced power while maintaining reliable chip performance. The clock distribution network delivers the clock signal synchronously to every sequential element in the chip, ensuring coordinated operation. Because the clock switches every cycle and drives a large capacitive load through extensive routing and buffer stages, it is one of the largest consumers of dynamic power, often accounting for 20 to 40% of the total chip power. Progressive buffer insertion and proper buffer sizing are essential to drive increasing fan-out while maintaining signal quality. However, unequal clock arrival times create clock skew, reducing setup and hold timing margins and affecting circuit performance. Interconnect parasitics further increase insertion delay, jitter, and power dissipation. Therefore, balanced clock tree synthesis, optimized routing, shielding, and clock gating are employed to achieve low power, high performance, and reliable clock distribution. Clock tree synthesis, or CTS, is the physical design stage that distributes the clock signal uniformly to every sequential element in the chip. Its primary objective is to achieve minimum clock skew, low latency, and reliable synchronization across all flip-flops. CTS automatically inserts and sizes clock buffers while balancing routing delays to every clock sync. Even in the presence of interconnect parasitics, it ensures nearly equal clock arrival times throughout the design. A well-optimized clock tree improves timing closure, minimizes setup and hold violations, and reduces clock uncertainty. Techniques such as balanced routing, optimized buffer placement, and clock gating also help reduce dynamic power consumption. The result is a high-performance, low-power, and reliable clock distribution network that enables stable operation of the entire ASIC. Power integrity issues arise from resistance, inductance, high switching current, and excessive current density in the power delivery network. Static IR drop is minimized by designing a strong and low-resistance power distribution network. Dynamic voltage drop is reduced using strategically placed decoupling capacitors that supply transient current during switching. Ground bounce and supply noise are controlled through low inductance routing and a robust ground grid structure. Electromigration is mitigated by using wider metal lines to reduce current density and improve long-term reliability. Self-heating is addressed through careful thermal-aware design, optimized routing, and efficient heat dissipation. Together, these mitigation techniques ensure stable power delivery, reliable timing, and dependable long-term ASIC operation. Summarizing, the reliable power integrity begins with a robust power distribution network that delivers a stable supply across the entire chip. Wider metal layers, sufficient power straps, and adequate via arrays reduce resistance and safely carry large currents. Decoupling capacitors placed near switching logic minimize voltage droop and supply noise. Current density must be carefully controlled to prevent electromigration and ensure long-term reliability. Power integrity and clock tree synthesis should always be optimized together to minimize skew, jitter, and timing violations. Finally, continuous IR drop, electromigration, and thermal analysis throughout physical design ensures reliable, high-performance ASICs with successful first-pass silicon. In this Part 2 video, we explored the impact of power integrity and clock distribution in VLSI physical design. We have also seen how reliable power delivery, power distribution networks, interconnect parasitics, IR drop, electromigration, and clock distribution network, contribute to stable and efficient chip operation. In the upcoming Part 3 video, we will explore other important physical design challenges, including signal integrity, power dissipation of active components, thermal characteristics, and ASIC reliability issues related to implementation of the ASIC. Thank you for watching. Bye for now, and hope to meet you in the upcoming Part 3 video.